All right. Apologies for my hoarse voice, but I just like to finish what we did in class on Wednesday or Thursday. So we talked about maximums and minimums of functions, and just to kind of review, if we have a graph that goes like this, well, we can talk about the absolute maximum, which would be the highest point that our function reaches on our domain, or we could talk about things such as a local max. Okay? And this would be a local min down here, and it's also the absolute min. So we talked about these ideas in class on Thursday, and we didn't get to this theorem, which is called the extreme value theorem, which is pretty cool. It says that no matter what function you have, as long as it's continuous and on a closed interval, then you're guaranteed to have both an absolute max and an absolute min. Okay? So let me just clear this slide and say that one more time. If you have a function that's continuous and it's defined on a closed interval, then you have to achieve your max and your min. And the idea is pretty simple. It's that, well, we have to have a filled-in circle on the left and the right, and whatever is going on in the middle, it has to be continuous. And so there's got to be basically the lowest point we reach. This would be our min. And then the highest point we reach, well, I guess in this case it's going to be over here. It's going to be the max. And so no matter how you draw your function, you're going to have an absolute max and an absolute min on your graph. And so now the question we want to think about is, where can this happen? So where can the local maxima and minima occur? And also maybe where can the absolute maxima and minima occur? So it's probably worth drawing a few pictures, right? What if my graph looked like this? Or what if my graph looked like this? Or what if my graph looked something like this? And we wonder, where can the maximum occur? Well, in this case, the maximum occurs somewhere in the middle, at this top of a mountain. In this middle one, our maximum occurred at the right endpoint. And on the final one, our maximum occurred at the left endpoint. And so our idea might be that max, min occur either at the endpoints of the interval or at a middle point, at a middle local max or min. So, okay, that seems pretty good. And now let's think again. I'm going to clear this page. If we have a local max or min, well, what has to happen with the derivative? Well, let me draw some local maxima. Right, here's one. Here's another one. And maybe here's one here. So, of these graphs, this one has a derivative of 0 because it's got a horizontal tangent. So I guess I could say f prime equals 0. And on these, we don't actually have a tangent line. Or if we do, it's kind of got infinite slope. Maybe this one has tangent line that's vertical. So we have that f prime is undefined. And we have a sharp point here, so we can't talk about a tangent line there. And so what's true, and this is another theorem, is that if we have a local maximum or a local minimum, then either our derivative is 0 or our derivative has to be undefined. And so this is summarized on the next slide, which says that if f has a local maximum or minimum at a point, then either the derivative is undefined or the derivative has to be 0. And these points come up so often that points with this property are called critical numbers. So critical numbers, these are the x values. I should emphasize that. So let me just draw a picture. if we had a graph that looked like this, maybe something like this, then the points where we have our local max or a local min or our point where the derivative isn't defined, these are going to be called our critical numbers. So if this is, maybe this is 1, and this is 3, and this is 4, then our critical numbers would be these numbers. Critical numbers. And so finally, let's put it all together. If we want to find the max or the min of a function, well, we agreed that it either has to happen at the endpoints. So step 2 says find the values of the endpoints on the interval, or it could happen in the middle. And if it happens in the middle, it has to happen at one of these points where the derivative is either 0 or it's undefined. And so what we're going to do is our plan is we find those critical numbers, we find those endpoints of the function, we're going to see what the height is, and then the largest is going to be the max, and the smallest is going to be the absolute min. So let's do a problem. Find the critical points, local max min and absolute max and absolute min of this function on the interval -2 to 3. Sketch a graph of the function. Alright, so you have some problems like this on the web work. So from -2 to 3. I like to draw my graph sort of straight away. So I'm going to draw it over here, -2 to 3. And I'm going ahead and plug in my points. So what's f of -2? Well, I could plug that in. I'm going to get -16, -12, plus 24, plus 1. So that's going to be negative 28 plus 24 is -4. I'm going to get -3. So if I draw this in, over here I'm going to be plotting this point down here at -3. And what about f at 3? Well, that's going to be 54 minus 27 minus 36 plus 1. These numbers are not very nice to me. So 54 minus 27, that's 27 minus 36 plus 1. That's 27 minus 35. So that's going to be -8. Right? So I could plot that over here. It's going to be -8. Okay? So I've got our two endpoints blocked. And now let's find the critical numbers. So if we want to find the critical numbers, so these are where f prime of x is 0 or f prime of x is undefined. Right? And our function is a nice polynomial, so the derivative is going to be defined everywhere. In fact, our derivative is going to be 6x squared minus 6x minus 12. And so if we want to know when is this equal to 0, we could set this equal to 0. We could factor this. I guess we can factor out a 6, so we get x squared minus x minus 2. And then we get x minus 2 times x plus 1 equals 0. And so we see that those critical points are going to be when x is 2 or x is minus 1. Okay? So let's see what our values are. Well, what happens at f of 2? Well, f of 2 is going to be 16 minus 12 minus 24 plus 1. Okay, so, oh boy, so it's going to be 4, and we add 1 is 5. We have 5 minus 24 is negative, 5 minus 24 is negative 19. So, oh boy, I guess we better make our graph a little bit bigger. So negative 19 is going to be down here. And so at 2, our graph is going to be way down here. And then what about at negative 1? Well, f of minus 1 is going to be 2 times negative 1 minus 3 plus 12 plus 1. So we check that's going to be 13, minus 3 is 10, minus 2, that's going to be 8. So at minus 1, we're going to be up here at 8. And our y-intercept, I guess if we care, is going to be in here at 1. So this is a really bad picture. You see I've sort of drawn everything over on top of it. But if I connect these dots, I see that it has to go in this shape. And so our absolute max is going to be 8, because that's the biggest it is. And our absolute min is going to be negative 19, because that was the smallest value that we had. And so we checked the critical points, we checked the endpoints, we took the biggest and the smallest, and that's how we found the max and the min. So thanks for watching. I think you'll get some practice on these problems on WebWork. You can always feel free to use a graphic calculator.